Gang. So, today we're going to cover two papers essentially, but both of them are conceptual in nature because we'll understand why exactly things work the way they do. So, of course, we'll be starting with this one, which is known as, yeah, this is known as Does reinforcement learning really incentivize reasoning capacity in LLMs? We all know that reinforcement learning itself is used a lot in terms of making things for physical AI, and that includes robots, self-driving cars, and everything. And in fact, when DeepSeek was launched a few years ago, the major thing that it moved around was the fact that it has some state-of-the-art reasoning and chain of thought just because of RL. And in this case, we are covering RLVR, and you're going to compare it that whether this actually helps in LLMs or is it all just a ruse and there's some other technique that helps us the most. That is, we're going to reveal over time. But yeah, the second paper we're covering today is LLMs can't jump. In a very simple sense, there are things that LLMs do when we ask them a question. If I say it wordly, deduction, induction, and abduction. But what is the toughest for an LLM? Abduction. And we'll come to that soon. So let's begin with the first paper. I have got my highlighted copy as well. Of course, I read my papers. But if you think about it, RLVR, reinforcement learning with verifiable rewards. So we need to figure out whether RLVR is actually being used and is actually beneficial for the LLM itself to increase its reasoning capability, comparing it with a base model itself. So if we have a normal model that is like, I don't know, let's just take Gemma for example, or like Quen in this case, like in the entire paper we're using Quen, so let's just reference that, right? So they are referencing to Quen 2.5 and it has various parameter sizes 7 billion, 14 billion, 32 billion, and 8 billion. Alright, sorry, Llama 8 billion. So when we move forward, we will understand that how they have created their experiment itself and how that has led to a much more clearer understanding of whether RL is being helpful or not, right? So let's just move forward instead of just yapping about the introduction, right? So as you're all aware, we have a base model, right? Anything which is already available. And then once we use efficient sampling, that is, we have the base model which brings out certain outputs, and then we sample those outputs and learn from them on the basis of reinforcement learning principles. I'll just leave it at that so that you are able to like catch up to things much quicker, right? What I need to understand in this case is whether the reasoning capacity of the model itself increases when we're using RL or not. And the way that they have designed the experiment is they have introduced a new term called K. So suppose I'm asking it a question that why is the sky blue? We're gonna get multiple and I would say plethora of answers from the LLM itself and then pick out the ones that gave the right answer, right? So K being the number of sampled outputs, all right? As long as our base LLM is giving us an answer, no matter how many passes it took, we're gonna consider it solvable. So to explain it to you in a much more simpler sense, if we are comparing a base model of say Quen and we're comparing it to an RLVR version of Quen as well, we are just comparing how long it takes for both the models to get out a desired answer. Suppose I'm solving an equation which is for a partial differential equation, right? The base model may take longer to find the right path to the answer itself, but as long as it's reaching it after a certain number of k passes, it doesn't matter, it is solved. So what we prove from that example itself, that the base model does have a way to reach to the right answer, and we compare it to the RLVR model. Now if I explain to you the entire proposition of the experiment itself, Since we are checking that whether the reasoning capacity is increased or not with the use of RL, if both the models are able to reach to the conclusion, no matter how many steps it takes or how many k passes it takes, that just means that they both can solve the issue. It's just that one takes a bit longer. That does not mean that the base model has a lowered reasoning capacity. So keep that in mind. Now let's just focus on major points from this entire stanza. I have the ones highlighted as well. I'm not going to do that for you. But in a sense, that since I've already described to you the entire experiment itself, but right now we're going to introduce our second lead of the story, that is distillation. Now, distillation, if you are not aware, is a very simple technique where we use a teacher model and a student model, and the teacher model, like I would say, uses its own learnings, and the student model learns quicker because it has access to the much bigger model and its weights. In a very simple sense, I'm like, I know I'm extremely wrong in a superficial technical way, but roughly this is the meaning. All right. Now, in terms of understanding the different RLVR algorithms, in this paper itself, we have discussed PPO. We have also discussed, I would say, wait a second, let me just. So, of course, they have discussed PPO, they have discussed GRPO, and they have discussed one more. I'm not able to, reinforce plus plus. So these three RL algorithms have been discussed in this paper itself. I'll give you a brief of them when I feel like it in this paper. But PPO itself was initiated or like made first by Sutton. I've met this researcher. He's an absolute gem of a person. He's comparatively much more senior in the field at the moment. But yeah, it was a great thing to meet him. But let's just move forward from the stardom that he has on me. Now, if I explain to you what is the scope of the experiment again, but much more technical in this sense, we look at this entire section. Solvable problems. Like I said, k itself is the number of passes we're going to make. So even if we have large k values, as long as it's being solved by the base model, we don't care, right? And we're going to compare it to distillation as well. So if I explain to you the major crux of the paper, we are discussing whether RLVR versus distillation versus a base model. What exactly is causing a greater reasoning capacity? All right. Now, another thing to ensure is that once we have that chain of thought that brings us to the right answer, we are also going to like check it by hand as well. And let's just move forward in terms of the results now. I think I've made you understand the basic experiment scope already. So like I told you, this paper itself will try to understand if all reasoning paths generated by the RL trained models already exist within the output distribution of the base models. I hope now you understand this question itself, right? And again, this is the major comparison point with respect to distillation as well, whether distillation expands the reasoning boundary or not, right? So instead of using short instruction response pairs, the training data consists of long COT reasoning traces generated by the teacher model. And by using these reasoning traces, we're going to teach our smaller student model, right? Hope it makes much more sense in terms of what we are comparing. And we got the answer that RL, that is fundamentally bounded by the reasoning capacity of the base model. Distillation introduces new reasoning patterns learned from the stronger teacher model. So, point to be taken, RLVR does not increase the model's reasoning boundary, it just increases the quickness of when we reach to the answer itself. But in this case, distillation increases the boundary of the data itself, right? So let's just move forward a bit. Yeah, I think this is like a bit more of a technical thing to cover, but Rollout is like the number of responses per prompt. And yeah, these are like basic terms. You can just give it a read if you want. And also entropy as well. What is the understanding behind entropy itself? The model's output entropy typically decreases as RL training progresses. That means that as RL training increases, the freedom of the model itself to choose different sorts of answers decreases. Right? That's why we call it as entropy. As you all are aware, what entropy usually means. So I think you can relate the terms at the moment. Right? And now we come to the major discussions. The key differences between traditional RL and RLVR, right? So I have made sure that these points are absolutely covered. But if I tell you in a much more broader sense, RL was usually, used for games, so that we are able to learn from our entire thought process of taking any step. But in the case of language-based models, the action space is so vast that RL is not that effective for increasing for like introducing new reasoning boundaries, right? And that's why we had pre-trained priors. Priors, if I say very in a simple way, is an algorithm, or is a, I would say, stick on the head of the LLM so that it creates reasonable responses. And it's a simple trade-off between exploration and exploitation. I will not cover that much at the moment, but I hope that you get most of the idea. But you can search up priors if you want more. I found this paper to be comparatively very, I would say, interesting compared to the ones that I've actually read before. But this is paper number 1. Let's just move forward to the second paper now. LLMs can't jump. This is much more philosophical in terms of its nature of the paper itself. The author is Tom Zahavy. But if I explain to you the difference, this one is a quick one. LLMs usually are very good at deduction and induction. Deduction, where we have a rule and a case and then we can predict a result. Induction, we have a case and a result and then we get the rule out of it, right? But the toughest part for an LLM is abduction, where we have a rule and a result and then we create a case out of it. Okay, if I explain to you this entire thought process of a jump, this is something which is usually very human in nature. Okay, I'll get to what it exactly means with the help of physics as well, but this is the major paragraph we need to focus on, right? Let me just open my second copy of the paper. So yeah, large LLMs have mastered the inductive compression of data and deductive verification of theorems. But to create an abductive jump required for scientific invention, we need world models. So this entire paper introduces world models need, that why is the entire industry running towards those at the moment. So if I compare to you, at the moment this is like an entire story of how mechanics is used, and then how special relativity came into being and how general relativity came into being. And the reason of discussion of these topics is to understand the human thought process and comparing it to, of course, the best minds ever that humanity has produced. That is Einstein, Newton, Faraday, you can name any if you want. But the major thing is how Einstein is relating to the topics that we just discussed. We first have an ideation phase, then we have a consolidation phase, and then we have a mathematical validation phase. Alright, now if I explain to you, if this is all just a story, I would say in terms of how we are comparing the human thought process to LLMs, but this is not that big of a thing to worry about. The main thing is to understand that abductive jump that is tough for LLMs at the moment. Okay, now here we have explained this as Einstein's happiest thought, when he got to know the understanding between special relativity and how the speed of light is compared to gravity itself. As we all know, gravity bends light, right? But that idea was very tough to process at that point of time. What is very interesting is that all of the scientists were, of course, understanding the system itself, and they were trying to deduce or induce this idea. But what they needed was to obtuse this idea, to have an abductive leap. And that is what makes Einstein different. And that is what makes us different from LLMs at the moment as well. And to progress AI itself, we need to understand what causes this leap in humanity, right? I know this sounds very, I would say, philosophical, but it is very technical as well. So, to make you understand the example and the thought process behind abduction, I'm going to take an example that is mentioned in the paper itself. As you are aware of the story, when Archimedes was asked to compare a crown and let us know whether the crown was made of pure gold, right? Archimedes was able to bring out the concept of volume displacement because he was sitting in a tub, able to understand the feeling of being floating, of being floated in water, right? He was able to connect the physical sensation of displacement and was able to connect it to existing mathematical theories of his era. This is abduction, the mental leap that humanity does on the basis of currently created topics. Nowadays, we have heard a few cases of abduction happening by LLMs as well as we grow much bigger in size. But this is talking about proprietary LLMs that we usually use, right? And this is very interesting to understand. For Einstein as well, he was just thinking about gravity, of how it feels to be an observer in a high gravity space. And that is why he was able to bring out the entire concept behind relativity. And this is all there is to this paper, trying to understand that what we need to expect from world models, what we need to expect from the entire thought process of the world model itself. It needs to learn how to connect the dots between physical sensation and theoretical axioms. And that's the entire point. So that's all from my side for this one. I hope I don't awkwardly end this video now. I'm showing way too much. So that is all. Let me just see how to end this. Yeah, let me just force way to do it. Bye bye.